Can you guys see what I just shared right now? Can you guys see that clearly? Can you see that?
Yes.
Yes.
Okay. Yeah, today we are actually going to start with a sampling distribution of the least square estimators. Now, if you remember from when we stopped last week, uh, we stopped because of um, we realized that we observed that when we take a different sample size from sample to sample, the values of the estimate of the parameters vary. And because of that, and when something varies like that, we actually need to get a sampling distribution of the least square estimators. So let me tell you that the essence of this topic, is just that we actually, because the values of the least square estimators do changes, and that is the reason why we need to do a sampling distribution of the least square estimator so that we can basically look at the mean. We can also look at the variance as well. Okay, and that will help us to do statistical inference. And that is the reason why today we are going to be talking about the sampling distribution of the least square estimators. And of course, you know, the essence of the sampling distribution of the least square estimator is because when I take a sample size 10, and when you take a sample size 10, of course, we're actually going to have different results, you know, in terms of values of regression parameters. And that is the reason why we want to look at the distribution of that. Okay. Now, the least square estimators, of course, you know by now, when I say least square estimators, I mean the formula. Estimators are formulas. Okay. So the least square estimator, of course, if I want to get a beta one, this is what I'm going to have, right? And of course, it's the same thing as the ratio of the covariance to the variance of X, as you can see right here. Okay. Now, if I want to get a beta naught, this is it. So what I'm trying to say, these are the estimates of that. Now, if these are the estimates of beta naught and the beta one and the beta naught, then we need to get a distribution of the least square estimators. We actually need to get distribution because we know that there are, you know, when I use a different sample size, or even when I use the same sample size, and if another person collect the same sample size, since we're going to be working on different participants, of course, the values of the beta one and the beta naught that we're going to compute will actually be different. And that is the reason why we actually need to know this. We need to have a probability distribution for them because their outcome. And don't forget that the probability distribution is a probability function, you know, that actually give probability for different kind of outcomes. Since we know we're going to have different outcomes when you make use from sample to, you know, when you vary the sample size. Now, what I'm trying to say right here is that, okay, the value of the beta one curve, you know, given the predictor is normally distributed with the mean this, and this is the variance. Okay. Now, what I'm trying to say here, the mean of the beta one curve is the parameter mean, because the parameter is actually going to be the true value. Okay. Therefore, when I have the different values for beta one curve, when I find the mean of that, that will give me the true value. That's what I'm trying to say right here. Okay. And this is the same thing as saying the expected value of beta one curve. Expected value of beta one curve is beta one. Okay. And this is the variance. Now take a look at what I have here. The whole of this is the variance of beta one curve. I'm going to walk you through how we can derive this. We can actually derive the variance to be this. We can derive the mean or to be this. And the same thing also go for beta naught cap. This is the mean of the beta naught cap, and this is the variance. Now, let me tell you something. The variance of beta 1 cap is different from the variance of beta naught cap. Look at the variance of beta 1 cap here, and look at the variance of beta naught cap. Okay? Now, let me tell you this. There's a sigma square here. The sigma square here is a variance of the error term. If you remember, we talk about constant variance. There is a difference between the variance of the error term, the variance and the variance of the least square estimators. Okay, I'm going to say that again. The variance of the error term is sigma squared. The variance of the response variable is also sigma squared. Let me tell you this. The variance of the, I'm going to say this again. You remember the other time when we did something? The variance of beta 1 is not sigma squared, but sigma squared divided by this. The variance of beta naught cap is not just sigma squared, but sigma squared multiplied by all of this. Okay? So I can give you data set, and I ask you to figure out what is the variance of the error term, what is the variance of the beta 1 cap, and what is the variance of the beta naught cap. But you know what? Before you can obtain the variance of the beta 1 cap and the variance of the beta naught cap, you must have obtained the sigma squared, which is the variance of the error. Okay? So what I write here now, what you are seeing now right now is the distribution of the least square estimators. Okay? And then we are trying to show the world that the distribution of the least square estimators of linear regression is normally distributed. And we have been able to specify the mean and the variance. Okay? This is the mean of beta 1 cap. This is the variance of beta 1 cap. This is the mean of beta naught cap. And the whole of this is a variance of beta naught cap. Okay? Now I'm going to move to the next slide. In the next slide right now, you can see here that, okay, I'm going to do this right now. Okay. Now, in the next slide, you remember the other time where we talk about the run time and the run size. Okay, you remember when we try to look at the relationship between the run time and the run size, where the run time is a response variable and the run size is a predictor. Okay, now, and you remember last time I also tell you that the assumption in a simple linear regression centered on the fact that there is a assumed straight line relationship between y and x. Okay, y is the response, x is a predictor, and I told you that x is assumed to be fixed. Look at that. And why do we assume x to be fixed? Fixed in the sense that it is given. When S is given, because the essence of building a simple linear regression model is that, okay, if I know the value of X, how can I predict the value of Y? And that is the reason why we are assuming that, okay, our X is fixed. By the way, what we're actually focusing on, what we actually want to predict is just a response, Y. Okay? In this case now, I want to believe that the run size is fixed and the run time is random. Okay, the response variable is random. Of course, as you can see right here, this is a scatter plot and this is a line of best fit. And of course, you know, we are able to obtain the estimate of the beta naught and the estimate of the beta 1. And what I have there is a fitted model. And we believe that when I plug in the value of X into this model, then I can actually fit the value of Y. Okay, that's our assumption right here. Okay, so now where I'm going right now, if you look at the assignment 2, please, you need to listen and be focused on this particular page, because you actually need the knowledge here to figure out assignment 2. You know, when you look at the assignment 2, I actually you know, there are some observations that are missing. Okay, and I want you to compute that out. Okay, now if I use R on the data set for runtime on and run size, okay, my data is on production. Okay, you know, you are into production and you actually want to predict how many time it's going to take you to run a particular size of whatever you want to produce. Okay, now using the arrow code, this is let's say this is a result. Okay, uh, this is the result. Now I want to show you some terms in this result. Okay, I actually want to show you. Now when you look at here, this has to do with the residual. Okay, what you see here happen to be is residual. This is just trying to tell me, okay, after fitting the model, I've already subtracted the actual values of y from the predicted value of y. Let me take you back. You're going to see something that I'm talking about. I've used this model. In this model, of course, you can actually compute your predicted. How am I going to compute my predicted? The predicted here is just like I'm having an in-sample prediction. I'm actually want to use the values in the run size. I'm going to be using each of them. I'm going to be plugging that here, and whatever I got, I'm going to be subtracting that from the actual value of y. Okay, of course, when I do that, what I have here is just trying to say this is a minimum value of the residual. Okay, and for your information, the symbolic representation of residual is E cap. Okay, so here is trying to tell me, oh, this is a minimum value, this is the first quartile, this is the median, this is the third quartile, and this is the maximum value of residual. Everything here is talking about residual. Okay, it's talking about residual. Now, when we come to this side now, this right here is a beta naught cap. What you're going to see under the estimate is a beta naught cap, and you know, under it you're going to see the run size. You're going to see whatever variable that this is going to be estimate of the beta naught, beta 1. This is a beta naught. Now, what I have here is also estimated, but these are standard error, the estimate of the standard error. This is the standard error for this one. This is the standard error for that one. Okay. And what you're going to see this side, let me tell you, if I want to get my t value mathematically, I'm actually going to do the estimate right here divided by this. Look at that. 149.74770 divided by 8.32815. That will give me the t value right here. When I do this divided by this, I'm going to have this. Okay. Automatically, it means that if I use this, if I do this divided by this, I'm actually going to get this one. And when I do this divided by this, I'm actually going to get this one. And of course, we can declare some values missing. Okay, you can declare some value missing, and now you're going to have a way to compute that by looking at the relationship between that. So the t value is a ratio. This t value here is a ratio of the estimate to the standard error. Okay, the t value is the estimate, is a ratio of the estimate to the standard error. And of course, if I want to get a p value right here, I actually need to do what is the p value associated with the test statistic, and I'm actually going to have that one. Okay, so that is that on that one. As you can see, I want to give you the notation This value here can be written as this. That is the standard error of beta naught cap. Can you see that now? That is the standard error of the beta naught cap, because this is the standard error that is corresponding to the intercept. Okay. Now, and when you take a look at this one, this is the standard error of the beta 1 cap. Okay, and this is the way it is written. Can you see that now? Okay, so I'm just trying to tell you what each value here represent in terms of statistical notation. Okay, and that's exactly what you can see right there. Now, take a look at this one, 16.25 right here, because you know everything here is actually going to come as a regression output when you make use of R. Okay, now the value here is estimated standard deviation of the error. This is sigma cap. Okay, this is sigma cap. Okay, and you know what, the sigma cap here, if I want to get the variance of the error, I only need to square this value here. I'm going to square the value. If I want to get the variance, if I want to get sigma squared, I need to square the sigma here. So what I'm trying to tell you here is estimated standard deviation of the error. Estimated standard deviation of the error. We can also call this standard, you know, standard error. But this is estimate of the standard error. Okay? This is the estimate of the standard error. But here, this is the estimate of the standard error of beta naught. This is the estimate of standard error of beta 1. But here, this is the estimate of standard error, you know, in general. And another name we can call that the estimated standard deviation of the error. Okay? And if you square that, that will be the variance. When you square this one here, that is what you're going to put. I'm going to show you some. I'm going to take you back. Yeah, when you square that, that is going to give you, this is going to be this. Sigma squared here. The sigma square here and the sigma square here. Can you see that now? Because an examiner I can actually give you a table like that, and I ask you to compute, to show me some statistical notations. Okay. Now, as you can see right now, this is the what? This is the estimated standard error. And this estimated standard error is based on 18 degrees of freedom. Okay? It's based on 18 degrees of freedom. Okay? If I want to know the total sample size is going to be 20, because the degree of freedom that we're using here is going to be n minus 2, not n minus 1. Okay? Now, and do you know another thing is that, do you know that the mathematical, if we want to use formula to figure out sigma, this one right here, if you want to use formula, you can actually start from here. You can first find the sigma squared. How can I find the sigma squared? You know, we can use this notation. You know what? The sigma square is more or less like the sum of square error that we talked about last week, divided by n minus 2. You remember the sum of square error? So the ratio of the sum of square error to the degree of freedom, n minus 2, is the sigma squared. Okay? I want you to have that in mind. Okay? Now, another thing that I want to talk about is this. Do you know that you can be asked to test how significant is the intercept? You know, intercept is beta naught, right? If I want to tell, if somebody asks you how significant is the intercept in a simple linear regression model, the very first thing I'm going to do, I'm going to write out an hypothesis. Okay, how significant is beta naught? Under the non-hypothesis, I'm going to say, oh, beta naught equal to 0. You know the meaning of beta naught equal to 0? Beta naught is not contributing at all into the model. Then I'm going to write the alternative. Oh, beta naught is not equal to 0. So beta naught is not equal to 0 means beta naught is significantly different from 0. Okay? This is the first thing that we're going to write when we are testing hypothesis against the beta naught. You know, I mean, when you are testing hypothesis on beta naught, this is the first step. You need to write this out. Okay. And after writing this out, okay, the test statistic value that we're going to use, I'm going to show you, the test statistic value is supposed to be our beta naught cap divided by the standard error of beta naught cap. The test statistic value is supposed to be this guy here divided by this guy here. Okay, that is the formula. The beta naught cap divided by the standard error of beta naught cap. So which means if I want to do that, I'm going to do 149.74770 divided by 8.32815, and that gives us 17.98. It means if I want to test this hypothesis right here, I need to first compute my t value. And after computing my t-value, and I'm actually going to check on the p-value. This is a p-value associated with this t-value. Okay? And I'm going to compare this p-value with the level of significance. The standard level of significance given is 5%, which is a 0.05. Now, when this value is less than a 0.05, we're actually going to reject the non-hypothesis. Okay, rejecting the non-hypothesis is just trying to tell you that this is where you are. It's trying to tell you, okay, the intercept is significantly different from zero. You know, intercept being significantly different from zero means that intercept actually contributes in this model. Okay, now the same thing that we do to, and that was why, take a look at that. You know, I told you the other time that if I want to test this hypothesis, the next thing you need to write, what is your test statistic? This is our test statistic. Oh, if this is my test statistic, what is my beta naught cap? I'm just going to take this guy here, minus, I'm going to write it here, minus 0 divided by this guy here. Okay, and that will give me the t-value. Okay, so when you do that, of course, you're going to have the result, and you can take decision using the p-value. And we are also going to do the same thing to the beta 1. Okay, for beta 1, you have to put beta 1 equal to, you're going to write this again, beta 1, beta 1. The test statistic for beta 1 is going to be beta 1 cap minus 0 divided by standard error of beta 1. So which is going to be this divided by this, and that will actually give you this. And you can actually use this to take a decision regarding that. Okay, so like I said, if you want to carry out hypothesis on the significance of beta naught and beta 1, please, you need to first state. You need to first specify your hypothesis formulation. This is your hypothesis. This one right here is for beta naught. This one is for beta 1. And you know what? Let me tell you this. When you are trying to test hypothesis, in the hypothesis, we don't write beta naught cap, beta 1 cap. What we normally write is the beta naught. Can you see? On the beta 1, we don't put cap on them when we are working with the hypothesis. So because parameters are the attribute of population, okay? What we test under the hypothesis to be population parameters. Do you get it now? So, and what is the significance of testing this? Why do I need to test for intercepts? Why do I need to test for beta naught in the simple linear regression model? What I'm trying to say is that the regression line goes through the origin. You know, the non-hypothesis is going to say, oh, that line is going to go through the origin. That is going to start from 0. Oh, this one here is trying to say, no, it shouldn't start from 0. It should start from a particular number other than 0. Okay, that is what this one is talking about. Okay, and what that means is that, okay, it means that the regression line is horizontal. Okay, I mean the regression line is horizontal. Okay, so I think you can see that now for beta naught. You can see that now for beta 1, because if beta 1 equal to 0, if your regression line is horizontal, then we are trying to say that you cannot actually use a diagonal line, a diagonal straight line. It's actually going to be horizontal. And horizontal means that when value of X increases, when the value of predictor increases, what do you expect your response to be? Your response is actually going to be 0. okay? And that's it means the model actually collapse, okay? And that is what you are testing right here, and I mean right and here. So here you are testing that the line passed through the origin, and here it is saying no, the line does not pass through the origin. And right here you are trying to say, oh, the regression line is horizontal, and here you are trying to say no, regression line is not horizontal, okay? And that's exactly what we are trying to predict, what we're trying to do right here. Now, the next thing we want to talk about is we want to use the relationship between the weight and the height. We want to use that to explain the assumptions of independence, okay? We got student 1, student 2. There are a lot of students right here, but I'm only showing you 4 students, showing you their weight and their height, okay? Now, if you look at the height, or if you look at the height and weight of student 1, that is exactly what you are saying. That is the height and weight of student 2, and that is the height and weight of student 3, and that is the height and weight of student 4. Now, when I say independence between observation, trying to measure the independence between observation versus independence between variables, you understand what I mean? So the assumptions of independence is actually looking at the way we are selecting these students, okay? The values of their the values of their variables of student 1 have to be independent from student 2, okay? The way we are actually going to do that. Now, in the last lecture, we used simulation results to show this. Take a look at, we're actually going to prove something that today, beta 1, I told you the distribution, because the values of beta 1 varies. It varies just because of the fact that when I use different data size, when I use different sample size, and then through simulation, even if I use the same sample size and I simulate like more than one, the value that I'm going to get for beta 1 will be different from the value in one simulation. Is going to be different from the values that I'm actually going to get from beta 1 in another simulation. And because of that, we now need to we need to get a distribution for beta 1 curve. Why do I need distribution for beta 1 curve? Because it varies. I can only seek a probability distribution for variable outcome, for outcome that varies, for outcome that changes, because beta 1 cap changes, and that is why we're trying to get the distribution for that. Now the assumption is that, okay, the distribution is going to be normal. Then what is the mean? Of course, the mean is going to be beta 1, and the variance of the beta 1 cap is actually going to be sigma squared divided by that. And you know what? Today we're going to prove that. Today we will actually prove that. Okay, that's what we want to prove today. Okay, now in the process of proving this, I need to be able to tell you that the sigma square here is the same thing as the variance of the error. What you can see here, var means variance. E is the error time. So the variance of the error time is sigma squared. Of course, I told you before that part of the assumption is that the variance of the error time is sigma squared. We got a constant variance, okay? And the SS that you see here is the sum of square deviation around the variable, okay? I have the variable x, okay? And this is the formula right here, okay? If you have a predictor variable, you find the mean, and you start subtracting the mean from each of the data points in that, then you subtract it, you square, then you sum, and that is that, okay? Just wanted to know about that. Okay, so one thing actually implies the other one. So what I'm trying to show you right now is just trying to, okay, what do you have here? There's a definition for each of these, okay? Now, because of that, I'm actually going to say, okay, beta 1 has a normal distribution. Now, if a beta 1 has a normal distribution, I call the mean of this is this. Another way to write the mean is to write expectation, okay? expected value of beta 1 cap given S is this. So what this statement means is that the mean of beta 1 cap given S is beta 1. That's what we're trying to say. Okay, and what we're trying to say right here is that, okay, the variance of the beta 1 cap given S is this. And of course, I've already shown you that sigma squared is the variance of the error term, and XXS, this is how to figure that out. Okay, so please study the formula very well. Okay, so part 1, simple linear regression, setup, and assumptions. If I have yi equal to this, I think I've shown you this before. Okay, I've showed you that before. And don't forget that the error time, there's an assumption that we place on that in the last lecture, where I said the error times can be summarized. You know, we got 4 assumptions, right? And those assumptions can be summarized as this. And this is like, okay, the error times is normally and independently distributed, you know, with mean 0 and variance sigma squared. Okay, the mean of the error is 0. The variance of the error is sigma squared. Okay, now having know that, then what is the implication for y given S? I think I also gave you the implication for that. So if I have this as a model, if this is my y, okay, and I want to get the expected value of y, that is the mean of y, okay, when I take the expectation of y, it's the same thing as taking the expectation of all of this, and that's why you have that one here, right? Okay, when the expectation multiply this and multiply error, of course, I'm going to have, when I split this one, when I use this expectation to multiply them, don't forget I said there are 2 components here, okay? This is the first component, the systematic part of the model. And this is the second component, the random part. So the expectation, we attract the systematic part, which is this one. Can you see that? The expectation, we attract the error, which is this one. And what is the expected value of error? The expected value of error is 0. Okay? So if I put 0 here, of course, and the expected value of this will remain this, because this is a constant. Everything here is more or less a constant, because the constant is not subject to variation. Okay? The expected value of a constant is a constant. And that's why I have this one here. Can you see that now? Okay? The expected value of the error is 0. That's why you have, can you see that now? Okay. Now, having know that, what is the variance of y given S? I've already know the expected value of y given S equal to S is the same thing as this. Now, the question now is, what is the variance of that? Don't forget that we're looking at the implication of this on the distribution of the y given X. Okay? Now, when you are looking at the distribution of something, okay, you need to figure out the mean and the variance. Now, this is the mean right here. Taking the expectation of that give us this. This is the mean. And taking the variance of that, you know, if I want to take the variance of that, of course, I'm going to do the variance of the model, you know, because the y is the same thing as this. Can you see that now? Okay, so when I apply the variance, you know, like I said, the beta naught plus the beta 1s is more or less like is a constant. Okay, and the variance of a constant is 0. A constant does not change. Okay, the variance of a constant is 0, and that's exactly why you're going to have 0 plus, what is the variance of the error? The variance of the error is sigma squared. Now, what is the implication? The implication is that the variance of the error is sigma squared. The variance of y is also sigma squared. Therefore, the variance of the error and the variance of the response is the same. I'm going to say that again. The variance of the error and the variance of the response they are the same. Okay, and that's exactly what we show here, right here. Okay, so if I want to conclude on the distribution of y given S, I'm going to say it follows normal distribution with this as the mean. This is the mean, you know, this is what we derive for the mean, and this is what we derive for the variance. Okay, I think you can see that right now. Okay, before I move to the next one, to the next page, is there anyone who need clarification? Is there anyone who need clarification? Let me read my chart. I think, do I have information in this chart? Okay. Let me. Okay. Somebody said, I have a question about the assignment. If we have time to kill it right now, okay. And somebody said, okay, let me take it one by one. The It depends on the. Do you want to ask question about the assignment 1 or assignment 2? If you want to ask question about assignment or about any assignment, you can actually ask that during my office hour, or you send a message to me and I'm actually going to address that. Okay. Somebody said in page 4, isn't the expected value of a E residual supposed to be 0, close to it, or is the median different from the expected value of sampling distribution? Okay, so if I get it right, you mentioned in page 4. I'm gonna go to page 4 right now, so that I will be able to see what you're talking. I will be able to see what you are really talking about. Okay, so let me go to let me I'm gonna go to page 4. Give me 1 second. Can you guys see my screen right now? Oh, okay. I think I have to reshare. I have to reshare my screen. Can you guys see my screen right now? Can you see what I'm projecting? Oh, okay. Okay, I think somebody said yeah. Now, if you look at your question, somebody in page 4. Okay, the question is not that clear. Can the person that chat with me right now, can the person, can you feel free to ask your question now? I'm on slide 4 that you talk about. What is your question?
Yes, hello. Yes, in the residuals portion, you have the minimum 1Q medium, 3Q max. The medium is 3.39. But
Okay.
isn't the average of the error supposed to be 0?
Oh, that's a very good question. We don't talk about median. When we want to figure out that, we use the mean. So the 3.329 here is just the median of the residual. So we don't focus on the median of the residual, but we are interested in the mean of the residual. So that's a very good question. I love that. Thank you so much for that. Have I answered your question now?
Yes, you have. Thank you.
You're welcome. Okay, so in case you have any question that has to do with what we're doing right now, you can actually ask and I'm going to answer your question. Okay, so let me go back to also in the absence of question, I'm actually going to go back to linear combination and proving normality. At times we could have a linear combination of the variables. Okay, I'll take a look at this. If U is a linear combination of W1 and W2, what are we talking about? The W1 and W2 are variables. U is a variable too, but U can be determined from W1 and W2. Why are we doing this? Because we need this to be able to derive something. What do we want to derive? You're actually going to see what we want to derive right now, because when you have the estimate of regression parameters, how do we come about the formula, the estimator for them? How can we derive the mean of the estimators, and how can we also derive the variance of the estimators? Because the formulas that we have, that we're using in statistics, we actually derive them. Okay, so And that is what I'm actually going to be showing you. I'm going to be walking you through how this formula had derived. Okay, and for you to be able to know that, then you actually need the knowledge of linear combination. Now, if u equal to this, if u is a variable and can be actually represented in terms of another variable, w1 and w2, but right here, c1 and c2 are constants. Okay, now, for example, if c1 equal to 2 and c2 equal to -3, okay, now u will be equal to 2w1 plus -3w2. Therefore, we can actually say u is a linear combination of w1 and w2. Okay, now having understand that right now, we want to have a goal, and the goal, what I wanted to show you now is that the beta 1 curve, which is the estimate of the beta 1 in a simple linear regression model, is a linear combination of the responses. And that is exactly what I want to show you right now. If something is a linear combination, of course, using the idea here, if u is a linear combination of w1 and w2, then it means we can actually write u in terms of this, where we're going to introduce a constant c1 and c2. Okay, now similarly, using this idea right here, if beta 1 is a linear combination of y1 up to yn, it means we're actually going to introduce constants c1 up to cn. Can you see that now? Now this is trying to tell us the beta 1 curve is a linear combination of the responses taken from y1 up to yn, and we're actually going to introduce constant c1 up to cn. Okay, now having know that, I told you the other time that the estimator for, if you want to figure out the beta 1 curve, this is the formula, right? I show you that this is the formula, right? And the numerator right here can also be called xy, which is the covariance parts, and this is xxx. Okay, now let us try to work on the numerator. Let's try to work on the numerator right now. This is, this is the numerator right now. If you try to expand, let me tell you something now. You know that I have a xi minus x bar. Okay, I can use this one to multiply y high here. This is it. Can you see that now? I can also use xi minus x bar to multiply y bar. Look at that. Okay, you can see that now. You like using this one here to multiply yi and using what I have here to multiply y bar until you can see that now. Okay, and if we have this using the distributive rule, you can see that in high school, when I have a into b minus c, if I want to use a to multiply, it's going to be ab minus ac. That's exactly what we have done here. Our a is xi minus x bar. Can you see that now? And that's what you use, so you can see how we come about that one. Okay, now if you have this one now, let us now use this summation to multiply this entity to also multiply this entity. Now let me tell you this. If there is any one of you who do not understand, please ask question based on what we're doing, because we're playing with notations right now. We're actually playing with notations right now. So this so now summation now acts on this. Can you see that? And summation also acts on this. Can you see that? Okay, now if you basically see what I'm doing here, this is the rule that I'm applying. If I have a summation on the addition of something, I can use summation to multiply each of that. That's why you see summation here, and that's exactly what we have here. This multiplied by this multiplied by this, we got this one, we got this one. Okay, now if that is what you have right now, another thing that I want to tell you is if you look at this, Okay, this is what you have right here. Can you see that? But if you look at this one right here, okay, if you look at this entity is going to be 0, and I'm going to tell you why. If you, I can ask you to show me this in exam. Can you prove that what I have here is going to be 0? How do I come about this? If you expand x, if you expand, it's going to be x y bar, okay, minus x bar y bar, okay. And when you expand further, when if this is summation x, okay, minus summation x bar y bar, because I have a x bar and y bar, the summation here is going to turn to n, okay, and it's going to be summation x n x bar y bar. So if you continue doing that, I can assure you, even before, even without multiplying, let me give you another way to show that this is 0. I'm going to tell you now. If you consider this one, summation times this, that is summation x, right? Summation times x bar. Summation times x bar is going to be nx bar, because x bar is not subject to variation. And when I use summation to multiply a constant, because x bar is more or less like a constant, it is this that is, that varies. Okay, so this is going to be nx bar. Okay, now, and what is summation x? Don't forget that x bar equals summation x over n. Therefore, summation x is the same thing as nx bar. So nx bar minus ns bar is going to be 0. So this entity right here is 0. Okay, and when it is 0, this is what you're going to have. Okay, so don't worry, I'm actually going to show you how we can prove that, again. Now, before I move forward, you can see that I've been able to express this. I'm still talking about numerator here as this. You can see that right now. Okay, now the next thing that I want to talk about is, okay, how can I find the mean of the beta 1? What are we targeting? What are we trying to show? See, what we want to prove, I'm going to show you right now. We want to prove that the expected value of beta 1 is going to be beta 1. Okay, this is what we want to prove. Okay, and how do we get here? I'm going to show you now. Now, let me show you. Expected value of beta 1 cap is going to be expected value. What is beta 1 cap? We said beta 1 cap is a linear combination of variable. Let me take you back on the linear combination that I talked about. Look at this side here. Beta 1 cap is a linear combination of variable. How can I write this one in short form? If I want to write this in short form, it's going to be summation CIYI. This one here. If I want to write this one in short form, it's summation CIYI. Okay? And that is the reason why I write this. Look at that. Summation CIYI. Okay? So summation CIYI given X. Because don't forget, what are we looking for? We're looking for the expected value of beta 1 cap given X. Okay? And the beta 1 cap is a linear combination of YI, and that's why I put that one here. You can see that now. You can see that right now. Okay. When you see this one right now, another thing you can do, you can bring the CI out, because CI is constant. You can bring it outside the summation. Look at that. You see the CI out now? Instead of having a CIYI, you are left with YI, right? You got a CI out here. When you bring a CI out here, now what is the expected value of YI given S? That is the model. Do you remember that the expected value of YI given S is this? You remember that? Okay. We're using this from the fact that we know that the expected value of Y given S is this, is the model. We talked about that before. Okay. Now, if I use CI to multiply beta naught and CI to multiply this, I'm going to have CI beta naught. Look at that. And here I'm going to have CI B1 SI. Look at that. Can you see that now? What did I use? I used the CI to multiply everything out. Okay. Now, after that, we are here now, right? Okay. Now, take a look at the last one. Look at this one here is what I copy to the next slide. The first, can you see that now? Okay, can you see that now? Okay, when you look at this one right now, okay, the next thing that we can actually do is, how can we have expression for beta naught? I mean, for summation C high. You know, look at it. This is beta naught here, right? The beta naught here is a constant. I'm going to bring it outside here. This is a beta naught, right? Okay. If this is a beta naught, then what I'm trying to tell you right now is that the summation the summation Ci, okay, the summation Ci is more or less like, is a summation x minus x bar divided by xxx. Okay, and if you take a look at this one, if I bring a beta 1 outside here, which is this one, then what I'm trying to say, don't forget that I said Ci is the same thing as, you know, as a summation xi minus x bar divided by ss. Okay, I'm using Ci to denote that. Okay, we're using Ci to denote that. I'm going to say that again. We are right here right now. Our Ci is going to be taken as sum of xi minus x bar divided by xxx. This sum of this divided by this is what we're taking as a Ci, and that's what I'm going to take as a Ci here. Can you see that now? And when you now have this one here, you're going to see that this guy here, look, if you take a look at what I have here, what is, can somebody tell me, what is the sum of xi minus x bar? What is the sum? What, this one is going to give us what? This one here. Can somebody tell me?
0.
Yeah, it's going to be 0 because the sum of deviation is 0. Okay? The sum of deviation is 0. Okay? Now, the sum of deviation here is going to be 0. That's why I have this 0 right here. Okay? Now, when you take a look at this one is not 0 because there's an SI here. If there is no XI and you have sum of XI minus X bar, you can call that 0. But before that, there's an SI here, you can't call this 0. This is going to hold. Okay? So this guy here is still this guy here. Can you see that now? Now, when you take a look at what I have right here, I think you know that what I have here, if you take a look at what I have here, summation xi minus x bar xi, okay? So what I have here is the same thing as this, okay? So, and that is going to cancel that. If this cancel that, I have a beta 1. Therefore, we have proved that the expected value of beta 1 equal to beta 1, okay? Now, the handout that I attached, you can see more of that in that lecture handout. So here, I'm just trying to show you how we can actually show that the expected value of beta 1 cap equal to beta 1, okay? That is a proof, okay? So like I said, the proof actually starts from this slide. Okay, you can see it starts from here, and we're going like that. You know, or let me just say it starts from here. But the reason why I'm going to say it starts from here is because I need you to know that where I get my CI wire. In fact, let me say it starts from here because you need the idea of a linear combination. Okay, so start from slide 9, slide 10, slide 11, and it's actually end in slide 12. Okay, it's actually end in slide 12. Okay, now that is how to prove for the mean, for the expected value. We can, the way to prove for the variance is also shown on this slide. Okay, if I want to prove the variance of beta 1, you know, the final destination for that is this one here. And how do we get here? We're actually going to proceed the way we proceed the other time. Okay, the variance of beta 1 cap equal to the variance of, what is the beta 1? Beta 1 is a linear combination of y and ci. So we're going to have summation ci yi. Okay, now when you have this one now, don't forget that this one here is the same thing as c1 y1 plus c2 y2 up to cn yn. You know, I'm just trying to write this one in listing form. Okay, This is in formula notation. Okay, this is in listing form. Okay, then I can use the variance here to multiply each of that. Okay, now look at that. Oh, variance of C1, Y1 giving S, variance of C2, Y2 giving S, up to the variance of Cn, Yn giving S. Look at that. Can you see? I use the variance right here to multiply everything out. Okay, can you see that? Okay, now, and the assumption is that the Y1, Y2 up to Yn are independent from each other. Now, another thing I want you to know, if you know, C1, C2 up to Cn, they are constants. If I want C1, a constant, to leave the variance, or to go out of the variance, then the constant is going to turn to square. Okay, so that's why you have a C1 squared, you got a C2 squared, you got up to Cn squared. Okay, if you have a variance of a constant with a variable, okay, the law says the constant is going to come outside the variance and become a square. That's a rule. That is the only condition to bring a constant outside the variance. Okay, look at that. We got this one now. Oh, when we get this one now, what are we talking about? Do you remember what I told you before? The variance of Y1 must be equal to the variance of Y2 must be equal to the variance of Yn. Do you remember the constant variance? It means I'm going to have C1 squared sigma squared, C2 squared sigma squared, up to Cn squared sigma squared. Okay, and since I have sigma squared, this one is sigma squared, this one is sigma squared, this one give me sigma squared, then I can actually write this, because the sigma squared is going to be common to each of that. What am I using right now? I'm using the idea, or I'm using the fact that the variance of the response have to be the same, has to be constant. Okay, and we're taking that from part 1, where we said the variance of y given x equal to small s is sigma squared. Can you see that now? And that is the reason why we got this. Okay, now when we have this one right now, I can bring my sigma square out. When I bring my sigma square to this side, then let me write this one in the formula form. You know, when I have a C1 squared plus C2 squared up to Cn squared, I can return that back to what? Summation Ci squared. Look at that. When I use that, do you remember what I used to denote my Ci the other time? This is what I used to denote my Ci. You remember that? I use this to denote my Ci. Okay, if I use this one to denote my Ci, then I'm going to put this one into where I have a Ci. Can you see that? Instead of Ci, I'm going to put the whole of that. Then I'm going to square that. Can you see that now? Okay, so this one here, SSS squared, if I bring it out here, I'm going to have this, and I'm going to have summation of x minus x bar squared. And what is the summation of x minus x bar squared? Is xxx. xxx will reduce this one, then I have this. Oh my God, this is the final destination. This is what we want to prove. Therefore, we have been able to prove that the variance of beta 1 cap is this guy here. Do we have anybody who need clarification? Is there anyone who needs clarification? Is there anyone who needs clarification on that? Okay, let me read my chat. Somebody said, do we need to know how to derive variance and beta 1 cap on exam, or just know how it works? That's a very good question. Let me tell you that start 3032 and start 5302, the two of them are basically we're actually going to test the idea of both theoretical knowledge and practical knowledge. Okay, we're going to test the idea of both theoretical knowledge and the practical knowledge. Okay, that's what we're going to do. But but the exam will be more of practical than theoretical. Okay, I can assure you that. Okay, and you know what? In your exam, uh, you actually, of course, there are going to be an instruction where we're going to ask you, okay, whether you're going to open notes and stuff like that. So I'm going to put that information for you today, and I'm going to tell you the modalities, you know, the way the exam is actually going to be. But what I need from you is this: if you don't really understand, if you don't understand something, I'm actually going to explain that to you. Now, somebody said, for part 4, are you saying the fittest slope beta 1 cap estimate value can be deduced from the population response parameter? Are we trying to infer the population parameter from the fitted model since population parameters are no? Now you said part 4. Are you what kind of slide? What slide are you really are you talking about? I want to know. Okay, let me see. If what you are saying is right here, if what you are saying is what I'm projecting right now, what we're trying to show, what I'm trying to say here is that, okay, since beta 1 changes, okay, you know, I've been able to show you that if different investigators should work on the same thing, they're going to have, even if they are using the same sample size, they're going to have different values of parameters. Okay. Now, if they have different values of parameters, and then we need to find the average of these values of parameters. The average of the value, what we're trying to say is that the average of the values will give us the population parameter that we want. Okay. Now, in part 4 here, we're now trying to show the world that, you know what, the mean of the beta 1 cap is going to give us the the population parameter beta 1 cap. That's exactly what we're trying to show. Okay, we're trying to show that if I have different values for beta 1 cap, and if I find the mean, then it will automatically give us what we need. Let me tell you something. Before we go into research, what do we need? We need beta 1. We don't need beta 1 cap. What we need is a beta 1, because the beta 1 is the population parameter. But we can never get what we need because we are not going to examine everybody in the population. We're going to take sample. But we believe that when we take different samples and we compute the beta 1 cap, the value of the beta 1 cap, we're going to have different values for beta 1 cap, and when we find the average of that, and that will give us what we need. Does that make sense to everyone? Have I answered your question? Somebody who I want to know. Oh, okay. Somebody said, now I think I'm happy about that. So please, feel free to ask questions. You pay for it. There is no question that is stupid as far as I'm concerned. No stupid question as far as I'm concerned. You can ask me any question. There is no any question that is stupid. Okay? I can take any question from you. You pay for this service. And you need to be served better. Okay? And that's why I don't hide your feelings. Okay? Let me use this opportunity to tell you guys that if you I've created office hour Wednesday and Friday. For those of you who want to ask question, you can. Do you know that you can also share your screen with me during the office hour? If you want me to explain anything, I'm ready to do that. Okay. So the office hour is going to be on Wednesday and Friday, and that will be from 12:30. Okay. So that is where we're going to have my office hour. So feel free. Okay. Do not hide your feeling. Okay. Okay. So now let me tell you this. Another question I may be expecting from you, you know, what we are trying to show in part 4 here is that, okay, since we are likely to have a different values for beta 1 cap, then we need to find the average. because expectation of that is like finding the average, and we believe that the average is going to give us the true mean. But remember something. How do we tell on the reliability of the average? To tell on the reliability, how reliable is the average, we need to find the variance. Okay, and that is what we're doing here in slide 13. If you look at slide 13, what is this? We want to derive the variance of beta 1 cap. We need a formula to figure out the variance of beta 1 cap. Okay, because we have been able to find the mean of beta 1 cap to be beta 1, then we also need to find the variance, because the variance of a beta 1 cap will enable us to be able to tell how reliable is a beta 1 cap. Okay, if we want to know how reliable is a beta 1 cap, and that's exactly what we're going to do. And what I'm trying to show you right here is to walk you through how to derive the formula to figure that out. This is a formula right here. This is how, I'm trying to walk you through how to come about the formula, because we have some of you that will take advanced, that want to come back and do masters in statistics, that want to go more in statistics, or that want to go more in biostatistics, or that want to go more in that. Of course, if you learn how to do this, of course, you'll be able to derive your own approach. Okay, if you want to derive a Newton, you need to know how they derive what is conventional. Okay, and so this is like walking you through how to derive the formula that we're actually using. Okay, now on the last slide, this is the last slide for this one, which means I want to give you the summary of what we have done today. What we have done now today, we proved that the beta 1 cap giving us follow normal distribution with the mean this and variance this. And don't forget that the variance of error is sigma squared. And don't forget the SXX here. This is how to figure that out. So our conclusion here is that, okay, the beta 1 cap has a normal distribution because the mean of that is this. The mean is like, okay, expected value of beta 1 cap given us is this, and the variance of that is this. Okay. Now, today I said we're going to go through through lecture material. Okay, so is there anyone who have any question before I go on to before I go on to the next lecture material? Is there anyone who have any question? So, like I said, there is no question that is stupid as far as I'm concerned. You can ask as many as any question you want to ask. Okay, so there's no question that is stupid. No question that is stupid. You pay for this service. Okay, and you deserve to be served better. You get what I mean, right? Okay, you pay for this service. So if there is anyone who want to ask question, you can ask. Is there anyone who want to ask question? Okay, if there is anyone, you can ask your question right now. Now, in the absence of that, I'm actually going to be going through, I'm going to be making it different. I'm going to be making a different lecture material right now. And the next lecture material that I want to, like I said, it's already uploaded. It's going to be lecture material, the second lecture for the day. So I'm going to do that right now. Give me 1 second. Okay, can you guys see my screen right now? This is the second material for the day. Can you guys see my screen right now? Okay, let me see. Yes, somebody said yes. Okay, I think I saw that on the chat. Okay, this is gonna be the part 2 I'm going to call that part 3. We are still on sampling distribution of least square estimators. What we did in the last lecture material is to be able to see how we can derive the mean and variance of beta 1 curve. Okay, is how we can derive the mean and variance of beta 1 curve. That was what we did in the last. Well, just that is what we did. Okay, now we're actually going to continue with that. Okay, in this lecture, we actually want to further, I want to give you detail on, how to use R to sample many times from the population. When you sample many times from the population, don't forget that even when you're using the same sample size, you're going to have the different values of beta 1, okay? And you're going to have a different value for beta 1 and beta naught. And that was the reason why I walk you through having a different value for beta 1 and beta 1 cap. We need to get a distribution for them. And that was what I just walk you through right now, where I show you the formula to be able to figure out the mean of the beta 1 cap and the variance of the beta 1 cap. Okay, you remember the other time I used a data set that has to do with the percentage of the vote received by Republican candidate in 2012 and 2016 election. We did that last week, where the counties in the United States was put into consideration. Okay, we want to make use of that data set again. And you know what? From that data set, we actually just want to put 10 counties, okay? We want to look at 10 counties, only that we're going to put 10 counties 2 times, okay? That's why you have the number of samples is going to be 2. The first time, I'm going to randomly select 10 counties, okay? The second time, I'm going to go there and randomly select 10 counties. Okay, when I do that, I'm actually going to have look at. I wanted to look at the first one right here. Can you guys see my screen right now? Can you see what I'm projecting right now? Oh, okay. I think I'm seeing from the chat. So somebody said yes. Okay. Now, if I decide based on the 2 samples that I choose, based on the 2 samples. When I say 2 samples, on each occasion, I choose a sample size 10, okay? And I draw the line. This is the line of best fit of the first one. This is the line of best fit of the second one. If having 2 different line of best fit is an indication that we're actually going to have different values of a beta naught and a beta 1, okay? Now, when I come to this side, if you look at this side, you can see that there's a lot of lines, right? It means I've chosen more than 2 sample size. If I want to know, I go into that and I choose 200 samples. What do I mean by 200 samples? The number of repetition is 200 here, but on each occasion, I choose a sample size 10. Of course, you expect me to have like I'm going to have a 200, I'm going to have 200 lines. You can see that? I'm going to have 200 lines. Line of best fit. Can you see that now? Okay. Can you see what I'm seeing right now? Now we get a lot of lines. Here, because the number of simulation is 2, right? I'm actually going to have 2 lines, but right here I'm going to have like 200 lines. Okay. I'm trying to show you what we do in research for us to be able to come out with the best value for beta naught and the beta 1. This is what we do. We do a lot of simulation. Here we are actually working on 10 counties in this here and here, but only that the number of time, the number of time we go into that population here is 200. The number of time here is 2. That's I got 2 lines here. I got 200 lines. Okay, very good. Now, when I increase that, look, if you look at the situation, this, you know, on this one and this one, the sample size is 10, but the number of simulation here is 2. But here, the number of simulation, the number of repetition is 200. Okay? When I vary my sample size, what happened? When I vary my sample size from 10 to 20, okay, and I do the same, okay, I vary my sample size. The sample size of counties I'm going to select is going to be 20, but I'm going to go back into that population 200 times, okay? So when I do that 200 times, what happened? When I do that 2,000 times, what happened? Okay? When I do that 2,000 times, what happened? So I'm going to be showing you the estimated slopes. Because what is it, though we know that we got 2 parameters in a linear regression, but we are interested in the beta 1 because it's the slope. It's the slope because it's the one that is going to tell us the rate at which the response variable is actually going to, you know, the rate at which is going to change with regard to the change in the predictor. Okay. Now, there's something I'm going to show you right now. I want to plot. What I'm plotting right now is trying to plot, you know, the density, you know, the estimated slopes. Take a look at this. The number of sample here is 20. Okay. And look at the other one. When the number of sample is 200, look at the distribution. When the number of sample, when the number of sample is 2,000, look at the distribution. Now, let me tell you something. What are we looking for? We are actually looking for a situation where the probability distribution of the beta 1 will be normal. If you compare the 3 shapes that I have here, okay, when the number of sample was 20, look at what I have. That is number of sample. This is not a sample size. What I mean here is that, okay, the number of time I go into that population. When I go 20 times, of course, you know, I'm going to have 20 values. For what? For beta 1. When I plot that, this is what it is, the distribution. When I go 200 times, I'm going to have 200 values, 200 number of values for the beta 1. Look at the shape. When I go 2,000 times, look at the shape. Now, the shape that we want is this one right here. Look at the shape right here. This is a normal distribution. Because we actually, one of the assumption is that our beta 1 must follow normal distribution. Can you see that now? So this is the estimated slopes when the number of repetition is 2,000. Okay? When the number of repetition is 2,000. So what we do in research, okay? If we do you know there's a way we can go 2,000 times into the data set that we already have, okay? So that will enable us to compute to have a different values of the beta 1. Okay, so this is so nice. Okay, because this follows normal distribution, and that's exactly what we need. Okay, now if you look at what I'm going to put something on them now, do you know that in a normal distribution we always want to find the average? And where can we have the average? The average is going to be at the center of the distribution. The average is going to be at the center of the distribution. And you know what? If you take a look at this one right here, if you take a look at this guy right here, this is a perfect normal. This is still good because of the fact that if you look at the average, if you look at the center right here is 0.99 and the center right here is 0.99, you can see that now. Okay, that is giving us, that is the center right now. And the center is actually going to be the mean of the beta 1. And that was why we said, what if the number of samples approaches infinity? Okay, what possible distribution could beta 1 have? Of course, when the sample is increasing, we expect from the theoretical statistics, from the statistical theory, we expect that the distribution of the beta 1 is actually going to approximate normal. If you look at this one right here, when this number of sample was 20, look at, you see what happened? This is not normal. This is not a good shape. Okay? I can't base my decision on this. No way. I cannot. But I gotta take my decision on the one that have a normal shape. Okay? Very good. Now, exploring the distribution of the beta 1 by observing the trend on the previous page. I'm talking about this page. By look at the trend, look at what we see. Okay, then we can guess that beta 1 cap has a normal distribution. Of course, you know situation where it can has a normal distribution. Okay, you can see that when we look at the samples. Then we can that actually confirm what we did before, that okay, the distribution of the beta 1 cap centers on the true population parameter beta 1. So which means what I'm talking about, the center right here, the center here, or the center right here represent the beta 1. Okay, the beta 1 is representing all the beta 1 cap. Let me tell you something. What you have from here to here is the value of the beta 1 cap. Beta 1 cap. But the center of that, if it follows normal distribution, the center of that is the beta 1, which is the true value. Okay? I'm going to say that again. There are so many values of beta 1 cap. When I find the mean of these values, that give me beta 1. The beta 1 is a true value that we're looking for. Okay? But we can only get that if we're able to get the accurate, capturing of the shape of the distribution. And it has to be normal. And what are we going to do, to make this to be normal is exactly what we're doing right now. Is what I'm trying to show you right now. Okay? So that actually confirmed what we said, that okay, the expected value of the beta 1 cap is beta 1. It means when I know the distribution of my beta 1 cap, that the center is going to be the true value of the mean, the true value of the beta 1 that I'm actually looking for. Okay, and that was why when I consider a sample size of 10 counties, and when you increase to the number, if the number of samples is infinity, like I said, there's a difference between this and this. We are still working on a sample size 10. We're working on 10 counties, but only that we go into that pool of data, because we are randomly selecting the 10 counties. Okay, so this is going into that population infinite number of times. So when we go into that population infinite number of times, we can actually attain the normal distribution for the beta 1. But you know what? We don't need to go infinite number of times. And as you can see right here, we only go like 200 or 2000 times. That's fine. We can use our R to do that. When you have your data set, let me tell you something. When the United States data set that I talk about, the election in 2012 and 2016, I can play around that. I can resampling with, around that data set. I can go into that data set and pick 10 counties in 200 occasions or in 2000 occasions. It's the same data set that I'm using, only that because I'm choosing at random, the county that will feature in one particular data set may be different from the one that may feature in the other one. And that is the reason why computing the value of beta 1 is actually going to be different from simulation to simulation. Okay. And so what is the takeaway right here? The takeaway is that when the sample size, when the number of repetition approaches infinity, of course, you're actually going to have a double bear shape. If you take a look at, if look at this is representing this right here. Look at that. This is the best. And the fact remain, we are going from 0. Going from this, something lower than 0.6 to 1.4. This is exactly what we have right here. Can you see that right now? That's what we need. That's exactly what we need. Okay, you can see a double bear shape. You can see the reason why I have to do basic review for you in statistics the other time when we started this course, where I was trying to show you the shape of a normal distribution. And this is the way we actually expect the shape of different values of beta 1 to be, beta 1 cap to be, before we can actually figure out the center. Okay? Now you can see the center on this one right now is 0.99. You see that now? Okay, can you see that is 0.99? Okay, so when you decide to move from sample size of 10 counties and you go to sample size of 50 counties, what happened? And you do different simulation as well. You know, the other time, let me tell you what we did right here. We are only focusing on 10 counties, but only that we go into that population so many times. But what if in a situation where I decided to increase that to 50 counties instead of 10 counties? Look at what I'm going to have. Can you see that now? This one is for 10 counties, and this is for 50 counties. And you know what? The number of times I go into that population was 200. Now, let me tell you this. You know, somebody may be saying that, oh, this is going to take a lot of time. Why do I need to get to, or why do I need to go to the population 2,000 times? Why not just 200 will be enough? But let me tell you something. For 200 to be enough, then it means we have to change our sample size for 200 to be enough. Of course, you know, 200 is not perfect. Look at the shape. It is 2,000 that is perfect. But you know what? We can still stay within 200 repetitions, but only that we can change our sample size from 10 to 20. And that will give us a better shape. Look at, and that's exactly what we do right here. I'm going to show you right now. That's what we do right here. Compare this shape with this shape. Okay? So we change from 10 counties to 50 counties, but we go into that population 200 times. Okay? Now, by observing the trend on the left, we can guess that the distribution of a beta 1 has dash variance as the sample size increases. And let me tell you something, as the sample size increases, we expect the distribution of the beta 1, you know, to have a smaller variance. When sample size increases, we expect the distribution of a beta 1 cap to have a smaller variance. And when it has a smaller variance, of course, you can actually see the shape of it. It's going to have the shape of a normal. So which means I do not need to have thousands repetition. But what I can play around, I can actually play around the sample size. Okay? I can play around the sample size. Okay? And that's exactly what you're trying to see right here. Can you see that now? When I'm using 10 counties compared to when I use 50 counties for, you know, and where I go 200 times on each. Okay? And look at the distribution now. Okay? So, what you're going to be doing next in the lab section, you're going to do a lot in the next lab section. My TA is actually going to show you how you can exploit this, how you can exploit that in R. Okay? Now we have done for beta 1. You can do the same thing for beta naught. Okay? We've done for beta 1. We can do the same thing for beta 1. Of course, you know, when you go into the data set, you can compute the beta naught and beta 1 at a time. Okay? So it's still going to be the same thing because we may be looking for the center for beta naught cap as well. Okay? And that's exactly what you are trying to see right here. The distribution of the beta naught cap has smaller variance and sample size increases as well. What happened to the beta 1 cap also happened to the beta naught cap in terms of decreasing in variance when the sample size increases. Okay? Now, We can also talk about the distribution of the least square estimator, the beta naught cap and the beta 1 cap. You know, we've talked about beta 1 cap. We talk about the distribution of that. We can also talk about that of beta naught cap. So I'm going to remind you of what we have done before. What you have here is the distribution of the beta 1 cap. And don't forget, we have been able to prove that the expected value of a beta 1 cap is beta 1. And the variance of this is this. We've been able to prove that, right? Okay. And don't forget, for beta naught cap, the expected value of a beta naught cap is this. The variance of a beta naught cap is the whole of this. Can you see that? So which means when you look at beta naught cap and the beta 1 cap, they have a different mean and they got a different variances. So most of the thing that you're actually going to be doing is to compute this from the data set. We're going to be computing this from the data set. And I'm actually going to show you how to do that. Like I said in this course, you're going to do a lot of computation, not theoretical, more of computation. I can assure you on computation, you're actually going to do about 85% of computation, while like 50% of theory. Okay? Now, of course, I'm just trying to show you what the SSS is, because in case you want to compute that from data set. And of course, the sigma square is the variance of the error. And why do we assume S to be fixed and given? I think I've explained that. Okay, I think I've explained that to you. Now, and don't forget what happens when the sample size n increases. I've told you, when the sample size increases, the mean of the distribution does not change. The mean does not change, but the variance changes. The variance will be smaller. Okay, the variance will be smaller. That was why I said the variance of distribution usually reduces, and that is when the sample size increases. Okay. Now, implication for using fitted regression model to approximate population regression model. Now you're going to see the implication right now. Number one, the estimated coefficients are unbiased. Now let me explain this. We are actually seeking to get a population regression model. But you know what? What we end up getting is a fitted regression model. Now, we got a way to justify that the fitted regression model that we have obtained using sample information can actually represent the population regression model we are seeking. How can we justify that? To be able to justify that, we need to consider the properties of a good estimator. And the number one properties of a good estimator is unbiasedness. And what do we mean by unbiased? The unbiased is just that the expected value of a beta 1 cap must be the same thing as the beta 1. Okay? And we have been able to prove that. That was what we proved. That was when I take you through here. I'm going to show you right now how to prove that a beta 1 cap is unbiased. Okay? That was what I proved in the first material. You know, in the first material that we did today, we said the expected value of a beta 1 cap equal to beta 1. I show you the proof. Okay, so let me just, this one right here. Can you see this one here? This is what we mean by unbiased. Okay, beta 1 cap is an unbiased estimator if and only if expected value of beta 1 cap equal to beta 1. Okay, if this is true, that is one of the ways to show that the fitted regression model will actually represent the population regression model. Now, take a look at what we're trying to say. We're trying to give a condition under which the fitted regression model can actually be used to represent the population regression model. And number one is that the estimated coefficient should be unbiased. And how can we prove that it is unbiased? We can prove that it is unbiased when the expected value of a beta 1 cap equal to beta 1. Okay, and another important properties is what we call consistency. consistency. What do we call consistency? Consistency is trying to say when the sample size increases, then we expect the variance of the estimator to be getting small. And that means it is more likely to get a estimated coefficient that is close to the parameter value, because it is when the variance of an estimator is very small than that that is a condition for the estimated value to be very close to the parameter value. And that is what we call consistency. The consistency as a property of I'm going to write that down for those of you that may not actually maybe understand my accent. I'm going to write that down. I said we got two important properties. We got two important properties of a good estimator. Okay, here I'm talking about regression estimator, and number one is what we call unbiasedness. Unbiasedness. And what we mean by unbiasedness is that the expected value of a beta at the expected value of a beta at should be equal to beta, and that is what we mean. And number two is what we call consistency. Consistency. Yeah, consistency. Yeah, and the consistency is actually talking about as sample size. As sample size increases, the variance, the variance, uh, the variance, the variance of regression, the variance of regression parameters, the variance of regression parameters will be getting smaller. We be getting smaller. And that is what we need. We actually want a smaller variance of the estimators, because when the variance is very, very small, of course, it means the estimator is reliable. It means the estimate of the regression parameter will be very close to the population parameter. Now, those are the two required properties: unbiasedness and the consistency. It's very, very important. Very, very important. And that is in that way that we can actually say, okay, fitted regression model can actually represent the population regression model. I think I have a chart. Let me look at my chart. Oh, okay. I don't have a chart. Okay, so the next thing that we're actually going to be talking about, oh, that is the end of that. Oh, so good. Okay, so that is going to be the end of the lecture for today. I need you to ask questions now. I want to entertain questions now. Feel free to ask me questions. You pay for the service. Feel free. Can you guys hear me?
Yes.
Okay, so feel free to ask me question. If you have any question, if you get stuck, or if you are struggling with any of the concept, you can ask me question now. Any question. Okay. In the absence of questions, I think silence means that you guys are good. Like I said, I'm gonna be having an office hour on Wednesday and Friday at 12:30. So you're also gonna make use of the same link. I'm using the same link for lectures and for office hours. And when you want to ask me a question in the office hour, you can share your screen if you need clarification on assignment. You can ask question, because I actually want you guys to be in good standing at the end of the day in this course, and that is the reason why I'm on grant. I'm on grant for you. I want to satisfy you. Okay. So whatever questions you have, you can actually bring that to the office hour. Okay. So I want to thank every one of you for attending my lectures today. I hope you guys enjoying it. And make sure you watch out for announcement. There's going to be announcement. You check the announcement section for new information. You check the canvas every time for new updates. I think I want to thank you for attending my lectures for today. I'm going to see you again tomorrow. Please make sure you stay safe and do have a good day. So bye for now,
Thank
guys.
you.
You're welcome.
Thank you.
Bye.
You're welcome.